So this is our last lesson of the whole school year, and we've already looked at polar form in the last video, and now we're going to talk about area and arc length and doing that in polar form. So first of all, what I want you to understand, if you need to get your books out and look at page 739 just to get visuals, that might be a good idea. Pause the video if you need to. But the idea is, instead of doing area under a curve, we're doing the area formed by sweeping that line across a sector. So it's like I'm doing from here to here in polar form. I'm going in that clockwise direction. So I'm finding the area of that pie slice, that sector. So reminder about area of a sector. We know that area of a sector is equal to 1/2 theta r squared. All right, reminder that the reason that is because you have that theta, whatever that angle is, over the whole pi, the 2 pi, the whole circle, times pi r squared, right? That's how we got the area. And remember that the pi's cancel, and that's how we're getting that as our area of a sector. Okay, now, if I'm going to do lots of little sectors, right, just like when we were doing area under a curve, we did lots of little rectangles. If I do lots of little sectors, right, and I add all of them together, so that means we'll be doing a integral. And think about what's going to be getting smaller and smaller, closer to 0. We want those pi slices to get smaller and smaller. So those are going to be smaller and smaller thetas. So we're going to have our d thetas. That's what we'll be going to infinitely small. All right, so what we get is the integral of whatever the function is. So we have radius squared, right? That's just the same as function, right? R is the same thing as f of theta. All right, and I'm going from one angle to another, so that's the alpha and the beta on our integral. The 1/2 we're pulling out, and then the theta is the d theta. That's what we're making smaller and smaller. So you can use either form. This one has r, this one has f. Okay, however you want to look at that. So that's how we do area in polar form. All right, at the bottom of page 739, look at that. It says the formula only works as long as f is always positive or always negative. It may or may not work if it's both positive and negative. So for this reason, we really have to be careful when we're doing polar form to look at the graph. All right, so I'm going to keep emphasizing that throughout polar. All right, so if we find the area of one petal of this rose curve. All right, so one petal, if you can either trace this out to see how it traces out, see when you do that, or you can do like a little T-chart. 0 equals 0, pi over 4 is 6, and then pi over 2 goes back to 0. So this traces out like this. Okay, so that's one petal. So I went from 0 to pi over 2. Okay, so that gives you your alpha and your beta. And then all we're doing is using the formula. So I have the 1/2 integral from 0 to pi over 2. My function is the r squared, so 6 sine of 2 theta squared d theta. And then we're just going to solve that integral. So I'm going to square the 6, that'll be 36. Bring that outside with the 1/2, that'll be 18. And I have sine squared of 2 theta. Remember from our integration techniques, if I see sine squared all by itself, I'm going to replace it with that double argument formula. So I'm going to double this angle, which is already doubled. So now I have 1 minus cosine of 4 theta over 2. And then we can split that up. So I'm going to take out the 1/2. So that's going to be 9. I'll have 1 minus cosine of 4 theta d theta. Now we're ready to do the antiderivative. So I have 9 times, this will be theta, minus 1/4 sine of 4 theta. Remember, we need to have the 4 here, so that would go outside of that, just for that part. And then that's being evaluated from 0 to pi over 2. Okay, so we've got, I've got pi over 2. This would be sine of 2 pi, which is 0, so that'll be 0. And then now I'm going to plug in 0, so that'll be 0, and then sine of 0 is 0 again. All right, so I just have 9 pi over 2. That's the area of 1 petal. Okay, so now what we're going to do is look at points of intersection on polar graphs. Again, look in your book on page 741 so you can see some nice visuals. We need the points of intersection to be able to find the area bounded by 2 polar curves. So here's the thing. If you look at the limacon and circle diagram on the bottom left on that page, you can get those points the points of intersection. So you can get the pi over 2 one, and you can get the 3 pi over 2 using algebraic methods. However, you cannot rely on algebraic methods alone. There's another point of intersection, and that's at the -1, 0. You won't be able to find that if you do algebraic methods. And here's why. If you look at the diagram right beside it with the globe, and it's talking about the satellites, satellites cross paths, but they don't cross paths at the same time, right? Otherwise they crash. But their paths that they have taken have to intersect, because otherwise we just have a bunch of concentric circles. So the same thing with polar graphs. Their paths might cross, but it may not be at the same angle. So if you do things algebraically, that's going to only find intersections that happen at the same angle. So that's why it's so important, again, to look at the graph. Okay, so if we're looking at the example 3, turn the page, example 3 on page 742, notice that they're trying to find the area between the 2 curves. Okay, so you see how it's between, they have the gray part and the pink part, the circle and the cardioid. So if I want to find that area, I have to know where that splits up. Okay, so I'm going to have the circle part from pi over 2 to 2 pi over 3. All right, so again, here's what I'm talking about. So from pi over 2 to 2 pi over 3, that's the gray circle part. Then you're going to add the pink part, the cardioid, and that's going to be the 2 pi over 3 until pi of the cardioid. Okay, so that just helps you. You're just breaking up that weird looking object into 2 separate parts, so you can say, okay, I'm finding the area under the curve for the circle and then the area under the curve for the cardioid. Okay, but finding that intersection is important so that we knew how to break up our integrals. Okay, so again, very important to look at the graphs. All right, so let's move on. Okay, so arc length in polar form. All right, so arc length is going to be very similar to the way we did arc length of parametric. All right, it's just we're going to have a little bit different formula. Now remember, in parametric, our arc length looked like this. We had an integral from a to b of, we had dx dt, and then dy dt squared. All right. Now, if you do a lot of substitution, because remember, our dx dt would be like our dx d theta in polar form. So if you plug all that in and simplify it, you get to this formula. All right. So I'm not going to spend time in this video doing all of that derivation. But if you do that replacement like we did with earlier with polar, then you get this formula. And again, this is the same thing as this. It's just they're using f of theta instead of r. All right, so either one is fine. Okay, but the main thing is if we're doing arc length, you want to make sure that you're only tracing that part of the graph once. So again, it's important to look at the graph and make sure you're only tracing it out once. Okay, so let's do an example. Find the length of this curve. So we have our r, and we're going from 0 to 2 pi. All right, so this one, if we trace it out, that will only be traced out once. However, it will be easier for us to evaluate this if we go, if we only do like the top half. Okay, so if I trace this out, okay, that's going to be the exact same as this green part. Okay, so we're just going to double that. So instead of going from 0 to 2 pi, I'm only going to go from 0 to pi. Okay, and then double that. Make sense? Because it'll be a little bit nicer. All right, so also something to keep in mind is if you, again, that whole positive negative thing, sometimes if you get negative numbers in there, it messes up your final answer, so you have to just be careful with that. So I don't know how many times I'm going to say it, but you just have to look at your graph, trace it out, make sure that it's only getting traced out once, make sure you're not dealing with negative values. All right, so let's use our formula. We're going from 0 to pi. This is our r. It might be more helpful to write this as 8 plus 8 cosine of theta. Then when we do our r prime, that's going to just be negative 8 sine of theta. Okay, those are the two values we need for our formula. And then we have this. Make sure you're squaring each of those. All right, so we've got some algebra and trig to do. So FOIL that out. And then I have my d theta. Okay, so all I did was square each of those parentheses. Now notice that here I've got 64 cosine squared, 64 sine squared. So this is like 64 sine squared plus cosine squared. And we know sine squared plus cosine squared is 1, so that's just 64. So I really just have 64 plus another 64. So this is going to be 128 plus 128 cosine of theta, which is a lot nicer. Factor out that 128. Okay. Now I'm going to factor out the square root of the 128. So if I do that and multiply it by 2, then that'll give me 16 root 2 square root of 1 plus cosine. Okay, so we've really simplified what's in the integrand. All right, so now what do we do with this? Well, if you see a square root of 1 plus something, maybe this is coming to mind. Multiplying the top and bottom by the conjugate. All right, so if we do that, then we will have 16 root 2 from 0 to pi, and then we'll have the square root of 1 minus cosine squared over the square root of 1 minus cosine. So what's great about 1 minus cosine squared? Well, that's just the same thing as the square root of sine squared. Okay, so now that means I'm just going to have the square, if I take the square root of sine squared, and then I just have sine squared. Yeah, just sine, not sine squared. Over the square root of 1 minus cosine theta. All right, so now what? How does that help us? Well, now at least I have a sine and a cosine in here, so I can do some u substitution. So what should we make our u? Probably the more complicated stuff down on the denominator. We don't ever want to have the du in the bottom, right? So my u will be 1 minus cosine of theta. Therefore, my du is simply sine theta d theta. Okay, so this is my du. And then I have the square root of u in the denominator. So that's going to be u to the negative 1/2 du. So we do the antiderivative, and that will be 16 root 2. And then I'm going to have a positive u to the, I'm going to not write u. I'm going to write to the positive 1/2 and then divide by that, so that'll be positive 2. All right, and then my u, I'm trying to do more than one right here to save us some time. My u is 1 minus cosine. So I did the power rule. I still had the 16 root 2, and then I replaced the u. And that's going to be evaluated from 0 to pi. Okay, so that's the integration part. Now let's do the calculation part. So we have 32 now, root 2, times square root of 1 minus cosine of pi minus square root of 1 minus cosine of 0. All right, so what's the cosine of pi? That's negative 1, so that'll be square root of 2, and then the cosine of 0 will be 1, so that will have 1 minus 1, which will be the square root of 0. Okay, so we just have root 2 times root 2, which will be 2, so that's just 64. Look at that. All of that comes out to be a whole number, 64. Notice that if we had done from 0 to 2 pi, okay, that would have given me the same thing. So I would have gotten square root of 0 minus square root of 0. Okay, so that's again that idea of I've got negative values going in there that'll mess up my actual. So we know that it's not going to be 0. We know that the arc length would not be 0. So if you get something like that, that's maybe an indication I need to use some symmetry to double it or something like that. All right, so now let's do area of the surface of a revolution. All right, so surface area. Remember that when we did this with our parametric, we said 2 pi from A to B, and we did the r of x function times arc length dx. Okay, so again, when we were doing parametric, that r of x would just be the x part. Now here, when we're doing polar, the x part is the r sine of theta. So you can see that this is the r of x part, or the r sine of theta. The arc length is what we were just doing. All right, so that's the formula from what we were just doing. All right, so you can see the parallels there. All right, and again, this is if you have your dy. Okay, so if you have your polar axis, that's acting like your x-axis. If you have the line pi or theta equals pi over 2, that's like the y-axis. Okay, so that's why that one has the cosine, and this is like the x-axis, and that's why we're doing the sine in that one. Okay, so you just have to pay attention to which axis we're rotating around. All right, so, and that's all of this is what I was just explaining, right? So it's just written. Let's do an example. I know I don't have one already in there, but let's do an example. Okay, so finding the surface area. Formed by rotation of r equals sine of theta about the polar axis. What do you think I'm going to say is important to look at since we're doing polar? Yes, the graph. All right, so if we graph this, this is going to be a circle, but it's going to be a circle that's up here. So it's a circle of radius 1, but it looks like this. Okay, so that's what r equals sine of theta looks like. Now, if I rotate this around the polar axis, here's some visualization for us. So I'm going to draw that down here, and it kind of looks like a donut, if you want to think of it that way. It looks like this donut shape almost. So it's these create some really weird shapes. So let me see if I can draw like a better donut. So it kind of looks like this, and it has all these curves coming out of it. Okay. All right, so just to get an idea of what we're finding the surface area of. All right, so remember to do the formula, we will need the r prime, which will be cosine of theta. All right, we need to know when it finishes its cycle. So to get all the way from here to here, that if you trace that out, that'll be from 0, so that'll be 0 to pi. Okay, so that tells us what our A and B will be, or alpha and beta. All right, let's do it. So surface area equals 2 pi, integral from, we just said it was 0 to pi. Then we're going to do r sine of theta, so that's sine of theta is the r, times sine of theta from the formula, and then times the square root of our r squared plus the r prime squared d theta. All right, so let's simplify this. So I have sine squared in front of the square root. Now here I have sine squared plus cosine squared, which is 1. So the square root of 1 is simply 1. So that's nice. That cancels out, and we have d theta. So I have another integral of a sine squared again. Hopefully you know what to do from the last one. So we're going to replace that with our double angle formula, 1 minus cosine of 2 theta over 2. We're going to bring out the 1/2. So that's going to be pi times integral from 0 to pi, 1 minus cosine of 2 theta, d theta. All right, so now we're ready to integrate. Remember, I'm going to need a 2 here, so 1/2 out there, but that's only for that part. So I'm going to have pi. Integral of 1 is just theta. Remember, the 1/2 doesn't affect that. And then I have minus 1/2 sine of 2 theta, evaluated from 0 to pi. Okay, so almost there. Let's do the plug-in. So we've got pi for the theta. If I do sine of 2 theta, that'll give me 0. And then I got to plug in 0 for theta, and then sine of 0 will be 0 again. So this is just going to be pi squared. Okay, so that's the surface area of the donut.